Ladies and gentlemen, good afternoon, and very welcome to EVA, and welcome to this seminar on artificial intelligence. My name is Magnus Breidne, and I'm the Vice President responsible for Foreign Affairs. And this event is in fact a collaboration between 4 organizations: the Embassy of Japan. You can't see this, but it's GSPS, and we'll soon get to know more about them. The Sweden-Japan Foundation, and also EVA itself. So the main driver for this seminar has been GSPS, who really is an important partner to EVA when it comes to supplying us with very, very good speakers from Japan. And I would like to ask Dr. Tsumoto to make a short presentation of GSPS. Please.
So, good afternoon, ladies and gentlemen. My name is Tadaharu Tsumoto. Yeah, already here. And Director of JSPS Stockholm office. As you know, JSPS and IVA holds a seminar once a year, inviting well-known or distinguished scientists from Japan. So today, I'm very pleased to see that Dr. Kitano is here, coming here, and so actually very pleased inviting him. Yeah, maybe later he'll talk about his own story. So he is a very well-known scientist all over the world. And also this time, I would like to express many thanks to Dr. Anders Lassnäs for joining us as a lecturer of these seminars. So thank you very much. Also, I would like to express many thanks to IVA offices here for arranging this nice, wonderful seminars. Thank you very much. And first of all, also, on this occasion, I would like to introduce some activity of JSPS Stockholm, just in a couple of minutes. That takes a long time. So, So JSPS was established about 85 years ago, as is shown here, and now JSPS is Japan's core research funding agency, or maybe the largest funding agency of Japan, and almost all the budget come from Japanese government, so a kind of semi-governmental funding agency of Japan. And so JSPS supports curiosity-driven research in principle in natural, social sciences, engineering, and humanities. And this just shows you some statistics of JSPS funds these days. So JSPS provides grant to research project to researchers at Japanese institutions or Japanese universities, regardless of their nationality. And last fiscal year, about total amount of grant was about 2 billion euros, covering 70,000 projects. And JSPS also provides fellowships. And last year, about 6,000 Japanese predoctoral graduate course students and postdoctoral young researchers were supported by this fellowship. And JSPS also promote international collaborations by bilateral or multilateral programs. And also, JSPS facilitate mobility of researchers by international programs. So last year, about 10,000 researchers supported from this fellowship program. And this just shows you activity of JSPS Stockholm office. And we hold seminars, symposia, and workshops with Nordic and Baltic and Japanese universities to promote joint researches and to stimulate student research exchange. And we collaborate with a couple of agency or academia or academic societies. So as shown here, IVA, IVA is of course one of the main partner institutions or partner academic societies. We also establish alumni clubs in the Nordic and Baltic countries. And this just shows you fellowship program of JSPS. So if you are interested in this fellowship program, please take brochure that placed at the entrance of this room. We just placed this brochure describing details about this program. And JSPS also have bilateral program between Japanese researchers and overseas researchers, including Sweden, of course. And actually, now, this year, 9 programs are running between Japanese universities and Swedish universities. We also have core-to-core program between Japanese core institutions and overseas core institutions. And now 3 programs are running between Japanese cores and Swedish cores. Okay, so this is the last slide. So if you are interested in the program just I mentioned, please ask us anytime. Also, as I mentioned, we place a brochure at the exit or entrance of this room. So if you are interested in this program, please take one to see details of this program. So thank you very much for your attention.
Thank you very much. Dr. Tsumoto. So we will start the seminar, and let me introduce the moderator, Staffan Trevet. He's the CTO of Recorded Future. But in this, and here at IVA is even more important because it's sharing the division number 12 in information technology. So welcome, Staffan.
Good evening, everyone. So back in 1950, Alan Turing, the British mathematician, formulated what's become known as the Turing test. And what he tried to do then was really to figure out a way, how can we decide if we have been able to create an intelligent machine? And his proposal at that time was that essentially you take, let's say, 2 boxes or 2 rooms, you put a machine in one and you put a human in the other, and you're allowed to have a dialogue and ask both questions. And questions could be of any kind. And if after a long enough time you have not been able to decide which box contains the human and which box contains the machine, then we can say, he said, that the machine is intelligent. Not a bad definition. I think it's still the best possible definition in many ways. So one of the things, I think one of the many things we're going to hear about today is a twist, I would say, on that. Dr. Kitano will talk about, which is called the Nobel Turing test. So what I'm assuming is that, without having heard his presentation, is that you take the same 2 boxes, you put an AI researcher in one box, and you put a human researcher in the other one, and if they both get the Nobel Prize, and you can't tell which one is the human, then you've achieved that goal as well. Is that a correct interpretation? Good. So, very exciting theme. This is actually the second seminar we're giving on AI at IVA. We did one a couple of weeks ago on how to create business out of AI, but this time then the focus is how to create research out of AI, which is perhaps even more exciting. So with that brief introduction, I'd like to welcome Dr. Hiroaki Kitano. And I have to use paper here because he's an extremely busy man. So he's president and CEO of the Sony Computer Science Labs, head of the Systems Biology Institute, group director for the Disease Systems Modeling Center, and also professor at the Okinawa Institute. But more importantly to me, who loves robots, is that he's also the father of the Aibo, a very cute. I have one myself, which I bought 15 years ago, and the battery has actually run out now. So I'm going to have a discussion afterwards how about I can get a replacement, maybe. Welcome.
Well, thank you. Thank you very much. Thank you very much. Okay, so we're gonna switch to my slide, I guess, here. Okay. Yeah. Well, thank you very much for your time participating in this seminar. And then obviously, my talk today, Nobel Turing Challenge, is very challenging and controversial, particularly in Stockholm, obviously. And I think this is very interesting, trying to be very stimulating and thought-provoking, and also like have a quite substantial essence in understanding how we do science and intelligence, and then how we actually achieve the autonomy. So like initially, actually, I proposed a challenge to build an AI system to win the Nobel Prize, particularly in physiology medicine, which I'm sort of mostly interested by, 2050. And by the way, this photo is from that I took when I was invited to the Nobel awarding ceremony back in 2002. And so, like, I thought this is an interesting challenge, and we're talking about it. And then actually, the reason why I started to, propose this challenge is a history of AI. If you look at the history of AI, the big part of the progress on artificial intelligence research has been made by the grand challenge. Try to build a machine that will solve the very intelligent problem, which actually even the human is difficult to solve. For example, like chess, 1997, IBM Deep Blue won the human chess champion Garry Kasparov. And in 2014, shogi, Japanese version of chess, were pretty much solved. And last year, Google DeepMind AlphaGo won Lee Sedol, which is top three, one of the top three. And then this May, Google AlphaGo actually beat like one of the best human champion decades, Kaketsu in China. And then a couple of days ago, they published a paper that they can actually build a machine that can beat any of the human and any of the previous AlphaGo without any prior knowledge, actually, which is completely groundbreaking. And so, like those has been made a big progress through the challenge that actually very intelligent mission to be accomplished by the AI that beat human capabilities. And also, IBM Watson's won a Jeopardy challenge. This is the quiz show 2011. Okay, so those problems, however, actually is a specific kind of problem which we call the complete information problem. That actually all the information necessary to solve the problem is in front of you. But basically, if you look at all the playfield, that you see all the information, and that's actually not hidden. There's no ambiguities. But just like a problem is so complex, it's a very vast state of space. And quiz show is a little bit different. You don't have anything in front of you, but you are sure that if you search, there's an answer because it's a quiz show. You have to have an answer. So this kind of problem now we know how to deal with. We need a massive data, massive computing, and advanced machine learning will be able to solve this, and we are actually able to create a machine that actually far superior than a human in those tasks. Okay. Now the challenge is actually much wider in a way that not all the information is available, and then there's a lot of noise and errors in the information we collect, and the multiple ocean moving simultaneously, no correct answers. Those like autonomous driving cars, or like a soccer game, which actually are doing the RoboCop for 20 years by now. Those are the problems actually facing the physical real world, and then we actually is dramatically different from the chess and the Go. And this is still not solved, and it's still like a very early stage. At the same time, those challenges will make a big impact in our society. At the same time, like a kind of intelligence we need for solving those problems is more reactive and in a dynamic, rather than actually deep thinking and discover something fundamentally important. I mean, of course, I'm not saying those are not important, but like a type of intelligence we need to solve that problem as opposed to scientific discovery is very different. So therefore, I actually proposed this Nobel Turing Challenge as try to get the Nobel Prize by AI. But of course, there's one of the audience in my early talk pointed out, Kitano-san, that's not possible. If you look at the Nobel's will, that will give it to the humans. It's not the AI system. So I have to think, okay. So then I come up with that little bit twist to the Nobel Turing challenge. The Nobel committee give AI system to Nobel Prize without noting that it's an AI system. Not it's an AI system. It's not the human scientists actually. So this is again interesting because that actually turned this problem into two sections. One is, can we build the AI system that can actually make a major scientific discovery? Okay. Yeah, the other is, can we actually, that system is autonomous enough so that we can be indistinguishable with a human peer. Okay, so that's actually interesting, because the problem of the Turing test was actually, that's actually the prize called the Robner Prize, and then I tried to actually exactly do the Turing test, is when you actually evaluate, like if there's someone on the other side of the screen is human or not, you're not really evaluating if the quality of the answer. It's more evaluating because of the typo or kind of backtracking the castle that if that is actually human-like or not. That was actually a critical part of the telling if that is a human or not. And because the human quality varies, right? So whether you're actually able to answer all the questions, maybe human or maybe machines, but a human can make a mistake. So it's almost impossible to distinguish based on the answer whether it's a human or the AI system. But at the same time, if a Turing test is testing at the highest level of intelligence, for example, a best scientist, I think that questions itself actually is very much more interesting one actually. So at the same time, I think it's more important to actually build the science, machine that can make a scientific discovery and redefine, we understand the entire scientific process rather than Nobel Prize. The whole point of framing this as a Nobel challenge, Nobel Turing challenge, is to be more inspirational and then just thought-provoking, rather than actually to get the Nobel Prize. Actually, it's because it's not the purpose of the science. Okay, so that's kind of interesting in a way. There's two axes for this challenge. One is we need to build a machine that is very intelligent. So this is the first phase of the project. Actually, we're going to have a more intelligent system help scientists. So it will be AI-assisted scientific discovery. This will be extremely important. That will accelerate the science a lot. At the same time, that will actually be the tool that we're going to use. So the question is, can we actually build an AI system that will actually autonomously select important topic, for example, or able to communicate with a peer so they can actually make a collaborations, or actually to be able to behave highly autonomously, just like independent scientists. That would be the autonomy challenge, and we have to really achieve this. Achieving this high level intelligence itself will be the accomplishment, but at the same time, then we're going to the uncharted territory, how we can actually build a system that is autonomous enough. Not just every time we don't have to tell the machine to do what, but a machine will actually autonomously discover something, important things to be solved. Okay, so at the same time, this is a systems biology challenge. Been a strong proponent of the systems biology. I published early papers back in 2002 and before. And, there's a little bit of research going on. At the same time, people struggling to do systems biology because it's so complex, and then also abundance of the data. We can do very defined systems biology in a small scale system, and then make some discovery using system science. But at the same time, if you go to the large scale system science, we don't have sufficient data. We're actually so complex, we won't be able to digest yet. So it's a kind of challenge from the systems biology side. Okay, now let me go back to a little over 20 years ago to just illustrate some of the point I make. This is one of the first research projects in biology that is, back in 1993 in a cellular senescence. So at that time, actually, the only available data was a gross kinetics, and then some of the genes, aging the genes expressed after the 80% of the lifespan of the human fibroblast, for example. So data was sparse, and we have to come up with a hypothesis. Try to have computer simulation to uncover the possible mechanism. So we actually at the time, like, there's some two-stage model of the senescence, cell senescence, and we propose this is not logically consistent. We propose like a two-process model. I'm not going into too much detail. That is not the important part. It's just like the important part is like a thought process. Then we actually, oops. It's not really, okay, this is something I need to go back. Then I need to actually come up with like a mathematical model, so that if that is actually two processes going parallel, we should have like a counter or master regulatory genes and probably effector genes, end result. So like if the two processes are actually combined by like controlled by the master genes and then two effector, or two different master genes, one effector group, or one master genes gene groups and two effector gene group, or completely independent. So like two possible models, right? And then also like after like a gene expressions target effector gene expressed, whether they actually work so autonomous or paracrine, there's 4 combinations as well. So like just a simple theoretical mathematical framework with 16 combinations. There are some other factors as well. So this end up having like almost 500,000 combinations of the mathematical model. So then what we actually decide to do is to create the computer simulations and then try to find out if any of the 500,000 variation of model actually can explain the experimental data available at that time. And the people are very skeptical, but I think we are lucky. We actually found some solutions. So we found a model that actually can reasonably reproduce the model. And furthermore, we were very lucky in finding out that only one variation of the model can actually reproduce this data, not any others. Okay, so we are very lucky. Usually we might have like a different numbers of variation equally good and have to select. But at the same time, this is only the mathematical representation, and you have to actually interpret what does that means in a molecular biology wise. So you have to actually interpret whether this mathematical structure means this molecule, or what is the molecular mechanism, like a telomere or chromatins or gene expression. And we actually come up with like some interpretation and publish a paper. And it turns out like this is the heterochromatin remodeling that actually controlling cellular senescence. That was a hypothesis. And then we published a paper, and then we specifically predicted, well, actually, it's not really prediction. We interpreted SIR2 in the yeast could be the really controlling the longevity of the yeast based on the mathematical model. But we have a lot of interpretations. And my colleague, Dr. Imai, actually moved to the MIT Rani Garante's lab, actually found out, actually confirmed that actually SIR2 is the longevity controlling gene. This is the beginning of one of the computational prediction story of the entire search engine family story. And that was, we have been very lucky in creating a model that is actually consistent with some actual molecular mechanism. We are actually very lucky in interpreting the mathematical model in a relatively accurate way. And so we actually, some of the model has been actually confirmed that actually exist. And then of course, like David Sinclair actually confirmed and then extremely confirmed this is actually the case. And then now we are talking about like searching overexpression mouse. This Dr. Imai's paper can increase the longevity of the mouse by 20%. And then we actually found out some of the substance called beta-nicotinamide mononucleic acid, MNM, can actually overexpress searching rather stably. And then we are actually now moving into the clinical trial in Keio University on this. So this is a great story. We are very happy, but at the same time, we start 1994, and the clinical study is we took 20 years for this. Okay, so this is a lengthy process, normal in biology, but at the same time, only systematic study we did actually is this part. We actually did all the systematic hypothesis generation, the computational model, and verify computationally and identify diseases. The all other part is actually depends on the intuition, actually. We believe this is true, and then we are only lucky that our interpretation or our intuition was right. That's actually leads to the clinical study today, but like if any of the interpretation or intuition was wrong, we couldn't get here. So like that means like a whole process of the scientific discovery really depends on the serendipity, by accident, and the scientific intuitions. And this is the interesting part of the science, obviously. We love that. We have a drama in there. And if you actually look at the Nobel Foundation's video and then interviewing the laureates and then half of laureates laureate actually answers, I was lucky. And then I discovered by accident. So like if that is actually true, you know, I think they are more confident than that, but actually they've been modest. But like, you know, we are really depends on the luck, on the scientific progress. And can we actually change that? And of course, like, you know, this is actually a photo took in a Cambodian textile factory and pre-industrial. But like if we have like a lot of machinery, like a sequencer or talk mass and all that, which actually give a lot of data in high precisions. At the same time, if we get the data, and we do all sorts of analytics platform. And then at the end of the day, we have to think, what is this? And we kind of struggle with the interpretation of the data. Okay, so that process is actually not changing, you know, many decades actually. So like we actually have a beautiful machinery to actually produce the data and then you know, visualizing. But like you know, final part of the science, like hypothesis generations, interpretations, you know, that part actually, I would say it's still the pre-industrial revolution level. I'm very, very provocative here, actually. You know, let's assume like if we are not really good in science, actually, you know, then what will be the remedy or how we can actually dramatically change the way we do science? And we are facing another problem because like this, you know, the senescence days actually, data was not sufficient. Data was sparse. But like now we have like 1.5 million paper per year in the biomedical area alone. Probably this is like a statistic 7 years ago, so probably having over 2 million papers per year. You don't have to read everything, but in a specialized area you are in, probably you're gonna have like hundreds of papers per day and you can't read it. And then this is actually a molecular interaction diagram of the immune system, part of the immune system. Two-like receptor pathway. We read almost 2,000 papers and get into all the details of molecular interactions. And you know, still, this is we built this 10 years ago, and we cannot update. There's no way of updating it because there's so much of effort and a lot of paper coming in, and there's no automated way of updating this kind of comprehensive body of knowledge. And this is actually a pathway involving Alzheimer's pathway, Alzheimer's disease, and we have with the 2,000 papers, very difficult to update anymore. And this is the E-cell cycle. Again, nearly 2,000 paper read. And this is probably a few years ago, and it's very difficult to update like this. So we are bombarded by the amount of data and the publications, and now we probably want to understand in as a whole, but there's no. It's very difficult, even just like an update. And then you know, this is all the manual process. We're now building the AI system to be able to read a paper, extract the knowledge rather automatically, and it's getting there. But you know, so far, it's been a really, you know, labor-intensive process, and it's and then also like not just like all the paper, but like all the experimental data and then the experiment that you do, and then you know, you have like a high performance sequencer, but at the end of the day you have all the pipetting and all those processes as well. And then how can we actually integrate that to make it much more automatic? And then also we depends our thought and communication in natural language. In our language. So that means like if you pick a random papers and random sentence, it says in contrast, in response to mating pheromone for one, CC24, blah, blah, and then you draw diagram. Well, okay, this represented this kind of molecular interactions, but actually, you know, from the nuclei to site problem, that's something we assume, but like this sentence or nowhere in the paper actually refer whether this complex will go to where. So we wrote this diagram because we know it's going to be the cytoplasm because we have biological knowledge. We have like some assumption behind it. And then whether this is the old form of the FAR120, CDC24 involved, you know, it's not there in the paper, but we actually leave those ambiguities, but they still can infer. That's the beauty of our creative cognitive process and the natural language. But at the same time, this leaves a quite substantial ambiguity because everyone interprets their own way. So like if that is a different, like we kind of misunderstood. And also like if you have like thousands of papers, 99 says one thing, if 1% says the other thing, the challenge is can we notice that? You know, if we notice that, are we going to ignore that? We consider this is like a very important discovery in a specific process, and then how effectively we can actually understand or interpret that. We're not very good at this actually. And also like a fundamental problem we're facing is, biological systems is basically high-dimension nonlinear dynamics. And then how we can actually describe this in a way that we understand and communicate is very challenging. If you even look at 2D, two-dimensional nonlinear area, you have to describe this, you have to actually set the axis, right? 2 dimensions. And then what is the proper axis? So any coordinates, we have to actually arbitrarily define, and then how you describe it and how you partition this. Otherwise, you cannot describe in a language. And then if you partition right closely, you're going to have a lot of errors. If you have a fine-grained partitioning, and then it's very difficult to communicate because each representations, descriptions will lose the semantics in our understanding. It's very difficult to understand. So there's trade-off on accuracy of the representation and the ease of communication, the level of the understanding we can have. And also, if you got the population dynamics, we are hopeless in understanding this. And now basically what is going on here is our cognitive limitations and cognitive bias. And a very famous researcher in the general semantics, Dr. Alfred Korzybski, says map is not territory. Map is our language space. Territory is a reality. Once we actually map the reality into the language space, it's not equal. We are actually involved in the bias. And also, like Berkeley Professor George Lakoff published a book called Women, Fire, Dangerous Things. Okay, what's the interesting title of the book is in one of the Aborigine tribe, woman, fire, dangerous thing is represent the same word. Okay, interesting what kind of culture it is, but no further comments on that. And then this actually leads into cognitive bias in the clinical reasoning. So this, this is the problem: is limitation of human cognitions. Is we are not good at digesting a very large amount of data and publications because we can't, and also the representing non-linear dynamical system in the way we can bring it in the thought process and communication, that we have like a natural trade-off on the accuracy and the communicability. So that's actually the serious limitations of our mind. And how can we actually fix that? And also system biology is getting situation worse because system biology, we talk about the large scale systems, non-linear. So maybe it's too complex for the human researcher alone. So maybe this is a science for the AI and the human hybrid system. Okay. So, but actually trying to have a machine discovery is not new. 1969, Joshua Ritterberg and Bruce Buchanan and Feigenbaum come up with a program called the Metadendra, which actually tried to come up with the scientific hypothesis for their mass spec data. And recently, Professor Ross King in Manchester created the ultimate, the robot scientist, which can generate a simple hypothesis in each genetics and then do the experiment by itself. And then a couple years ago, last year, this dark reaction project is actually getting a lot of experiments that failed, and suggesting what's next. And then that helped the researcher a lot. Okay, so, but at the same time, I try to get the moonshot and a kind of big goal. Those research is very important. But at the same time, having a high goal actually will accelerate the science. So we try to actually, just like an Apollo project, which requires vision and theory and technology platform management, and push the things forward. What happens if we actually get a Nobel Turing challenge? Then what would be the theory? What would be the technology platform required? And what would be the kind of management we need? We have to think about it if we have to actually really embark on a challenge in a serious way. So a theory actually would be, let's assume the science is all about massive generation hypothesis and a fast verification process. And of course, we have to create a hypothesis rather wisely, rather than completely randomly, and then how fast we can verify is going to be challenging thing. At the same time, if you look at the history of artificial intelligence, people thought chess cannot be solved by the search, by the learning, because you need human wisdom because things is too complicated. And the same thing I said in the shogi, same thing was said in the Go, but actually at the end of the day, how we solve the problem is a massive computing, massive search, and of course it's not completely random, but very wide search. It's not really human intervention. The lesson from the AI challenge was human knowledge actually harms. Human knowledge actually undermines the quality of the solutions. So that's actually, if that is actually the case, if we take a very, aggressive positions, scientific discovery is exactly the same. okay, let's forget about the human knowledge, probably not entirely, but let's assume like try to get the big search space generations, hypothesis generation, and the verification. That could be the new form of scientific discovery. That would be very interesting. And you might actually ask, asking right question is very important in science. Okay, so, but at the same time, like it's very important to understand, this is very important if you have a limitation in the career span and the resource, then you have to ask right questions. Otherwise, you are not going to be successful. But if those resource limitation is not there or was significantly reduced, asking right questions will still be important, but probably relax because you ask a lot of questions. Right question maybe in those questions. So that because of the availability of resources and how quickly you can go through all the hypergeneration verification questions, things are going to be very different. Okay. Now the standard platform. I think I'm spending quite a bit of time. I'll probably skip very quickly. And we've been building actually a platform called the Garuda platform to actually be able to smoothly interoperate multiple analytics tools and then the devices. I mean, just going through it. One of the examples that we actually used the Garuda for is a JSPS funded project with the try to get the atomic PK model and electrophysiology had and try to predict the drug-induced arrhythmia. And then we actually create like multiple tools and try to get the physiological model, the molecular interaction models, and then get all the heart model, and then multiple software combined together very smoothly with the platform. And we got this electrophysiology, and this one's another one you see. This is a normal heart, and this is a heart with like this is a specific drug, and then there's a spiral web. This is arrhythmia going on. Well, this kind of thing is very smoothly can investigated within probably this one requires 8 different software to seamlessly work together. Okay, so another I think example is collaboration with Professor Kawaoka on the influenza drug discovery. This is like a big model, and then we actually do the network analysis, and then we come up with like a multiple possible high priority target, but analysis, and we actually use the machine learning based docking simulation. I'm not going into too much in detail. And we actually have the machine to actually able to tell which actually docking simulation to believe in a specific compound target pair and come up with a very accurate predictions, and that actually result in the very good prediction of the possible target and then the compound among the very large list, and now also getting the clinical trial. So like this requires like 6 or 7 different software to work together, particularly computer simulation, network controllability, and machine learning. And so like this pipeline, for example, can be automated. We do this in human, but like that can be something we can automate. So we have like a lot of variety of tools and connectivities, and so like a software. So those softwares are already there. I mean, just skip. And then we have a lot of collaborators and users, and then we have like a computing platform, and we are actually moving collaborating with a robotic system to do the experiment. So this is collaboration. This is a robot in Yasukawa Electronics, and then this one is in ICE, Japanese research agency, to be able to automatically go through the experiments by itself and getting it very accurate rather than a human technician to carry out the same experiment. So its basic infrastructure is getting there. Okay, so then they put the intelligence on top of that, so we can actually, intelligence system can actually go through the whole process. So there's a 2 point which is very important. One, AI may be able to recognize the pattern that the human cannot recognize. And this is a very famous chart for how a deep learning network will be able to detect automatically detect the cat's face, and the famous Google cat. And then this is actually all the basic of deep learning neural network, and I'm going to go into the detail. But one of the things which I find interesting is that this is a paper which actually published a few years ago, is deep learning network actually showed the original image like this, and it says it's school bus. And this one, the deep learning network says it's ostrich. Okay, if you think this is ostrich, I mean, you gotta be in the hospital. But actually, this is not exactly the same. It's a slight noise in it. This is a noise amplified 100 times. And if you look at this very carefully, I mean, you look like, maybe if you look ostrich face. If this part looks like somewhere over there. But why? I mean, this must be actually in internet. There's a little bit internet, image like this in the internet. Like this neural network actually must have like this one of the training example. Then it's possible they actually match this and get some certain probability. This is actually matching. So like in this case, this was actually the paper actually trying to demonstrate the instability of the deep learning network. But it'll be interesting. This might be a counterexample of the utility of this kind of network because it may be able to see the pattern that we won't be able to see. And if we apply this to the clinical data, for example, I'll probably skip this. And then one of the study we did with the Tokyo University Hospital was to get the rheumatoid patient data and then classify, bring all the subclass of the rheumatoid patients. And this is actually all the dot is a patient, and then we actually remove the doctor's diagnosis to get everything about the diagnosis data, and then automatically classify, create a subclass. And then that, if you look at this, like those could be outlier, this could be a new subgroup, and then those are the things it's very difficult to actually detect without like this kind of data-intensive machine learning. And if actually this is a new subclass which doctor haven't recognized, and then what is a biomarker? If there's a biomarker, that could be actually very precise personalized medicine opportunities. So, those things actually it's relatively well understood, but I think they'll be very effective as a part of the the functionality. But I actually think the big question is, for the science we want to ask for the creativity. Can the AI be creative? Okay, so one of the things is this is AlphaGo. This is very interesting. If you look at the AlphaGo game against the humans, sometimes the commentator says the computer made a mistake, and 10 moves later, it turned out this is a brilliant move. And the reason why that happened is that human play in a corner because we can't compute in the center. So like from the human commentator view, that the move actually was weird because it doesn't contribute to getting the territory in the center. But AlphaGo actually trying to get the center. So they actually play against each other, and they get billions of games that actually possibly play more on the center that human have never exposed. So that's and then after this AlphaGo, DeepMind actually disclosed some of the move by AlphaGo against AlphaGo, and we are shocked because that is not a kind of Go we play. It's a very different kind of Go we haven't ever seen in the history of Go. And that's strong. So that means we thought 3,000 years of history ago, we thought we are going to the really top-notch in the Go strategy, but it's just kind of lower level compared with what has been discovered in AlphaGo. So the key was actually this kind of self-play, and they're actually generating a lot of actually unknown games that the human never played. So we talk about a big data, but a big data is important to get the resolution and rare cases. But what is very important is not just the data, but also the data generations. That actually is a lot of hypotheses kind of move and then evaluating it very quickly. So that's actually AlphaGo actually experiencing the kind of world that we humans have never experienced. And that's where the strength of AlphaGo. And actually, so that means actually human play games, and then if you got the data, all the possible movement go, then AlphaGo actually switch that and it go beyond what the human have done. But actually, 2 days ago, there's a more striking, paper published. They actually did achieve this without having any of the human data. So no history, no past record of the Go, and just random play, reinforcement learning, and then deep learning, and they get there in 3 days achieve the probably best performance. So that's kind of interesting because what the interpretation of this is the AlphaGo original versions before AlphaGo 0 was actually constrained by the initial data because this is what the human did. And they trained based on that. So a system is biased toward how human play the Go. And now AlphaGo 0 eliminate that. So they actually start possibly exploring the kind of space, unbiased by the human experience. So and that's actually stronger. That's kind of interesting because getting rid of human knowledge make machine much stronger. And this is actually also, it's frightening because we believe our experiment is very important, but it may not be actually the truth. Okay. Let me go to another example, and I probably have to finish in 5 minutes or so. Can you actually get the sounds? Yeah. the music actually created by the AI system called the Flow Machine, our Sony Computer Science lab in Paris. And it sounds a little bit like a Beatles music, as if you notice that. And how this has been built is actually, we actually put the 14,000 read seat and they get the machine to learn what is the motion, movement of sound that sounds like music to us. And then the composer who actually used this system actually put, in addition, 55 songs of the Beatles, so that machine learned what is the movement sound specifically that sounds Beatles to us, and they generate this music. Okay, so and then they put it in YouTube last year, and it got very popular. And what's going on is if you get all the state space music, which is vast, and now this actually machine is discovering because they learn the style of Beatles, it's generating the sounds of song Beatles-like song, which Beatles haven't discovered, because Beatles actually compose very small portion of the song that could be sounds like a Beatles to us. Okay, so that's kind of interesting, and of course, like we put depends on the how we tune the system. We can have a very different song, and we actually got the concert last year in Paris on this, and then just like probably 30 seconds on this. This is a very different type of music. It's still pop music because this is the whole tune for the pop. I don't think I have the time to actually go through, but like even for the introduction, you can see this is very different from the Beatles music. Okay, so and what is happening is actually that we actually expand the seed, but at the same time, like it's possible like if you get rid of all the music, the Beatles seed, human knowledge, we can this machine will be in a very vast space, which is actually outside of the movement sound. That doesn't sound like a music to us. The problem is how quickly actually eliminate this part. So like scientific discovery is like this. Scientific discovery, we can actually, based on the knowledge that we discovered, and then we can actually machine to generate a lot of possible knowledge or hypotheses. And then probably we can actually, based on what we have known, we can probably, machine will probably come up with like a lot of hypotheses the human can discover and the human can understand. At the same time, there's no guarantee that scientific truth is written in a way, it can be described in a way that the human can understand. There may be, probably for sure, it's a lot of knowledge that actually scientific truth is not in a way that we can probably comprehend. We probably have to comprehend in approximations. And if you look at the web, Amazon or like the recommendation rules, if you have opportunity, but those rules does work. But like if you look at the rules, we don't understand what they're talking about. It's very complex, and in a very complex rule, it works. So like even in that e-commerce aspects, like something that work is not necessarily in the way that we can comprehend. So that's kind of interesting, and then see how it goes. But like a challenge here. Not unlike the goal, which actually can evaluate rather quickly. In a scientific discovery, the question is how are we going to generate a hypothesis which is actually beyond the rule of goal and how to evaluate. That actually very important to actually have the proper simulations to be able to generate the hypothesis and then actually check. And then I have like all sort of implication of this, but I think I'm kind of running out of time. So we're going to skip this, but I think it's very important is if once you got the okay, so commodity, getting AI, it's commoditized. So you have, for example, like if you want to ask like some technician to do something or ask scientists, you only can reach like a scientist you know. But if those knowledge or skills being put in the AI, that can be copied, that can be commoditized. That actually have the significant bigger influence on the way we do science. And then so like it's be the crowd-based science, and then we are putting all the robotics to the skill, and probably a knowledge system to be the way we think that we discover. And I think this will have a profound impact in civilizations, because progress civilization and progress of tools. And from the bone and stones to industrial revolutions, information revolution. Now, a lot of people talking about machine that think, or smart, but we're talking about the machine that create knowledge, and that I think would be a fundamentally and qualitatively different kind of machine that we're going to get. And so I think it will be a very important challenge that we embark. But at the same time, if we build a system, we have more challenge, because we have to go and get award. and then we have to have the banquet and have a reasonably good chat, and which is very challenging, more than the scientific discovery. And we have to dance, and that's tough. And you think this is crazy, but I think someone who's crazy enough will be change the world. And then if you think you are crazy enough to embark on challenge, just let me know. I'm trying to get more people to get in the challenge. Thank you very much.
And I must admit, I do hate to interrupt you. It's so exciting. So I think we have time for 1 or 2 questions while we switch computers. Is there anyone up for some question? Yeah. Okay, I'll ask a question then. So of course, at some point here, the results of your AI researches will be, as you said, beyond human comprehension. So how can we trust them?
Well, that's actually it's important, because we have a big issue even now. Like a deep learning neural network actually provide a much more accurate result than the human do, and it's black box. So a lot of research going on in what we call explainable AI. Can AI explain the reason of the decisions? Okay, that's one. The other thing is actually, in a science, probably we have to actually understand by approximation, because some of the principle may be too complicated, and then approximation only a handful of people understand. But in that case, we trust those people who understand. Right, so it's just shifting from the someone for the expert. We trust them. We trust the AI system, and it's just a shifting who we're going to trust, and that's probably depends on their track record and then all the social acceptance.
Okay, so could you even, with the different AlphaGos, could you have a hierarchy of things which you trusted? You trust the lower levels, and then they trust the
probably
higher ones?
Starting from the very low level and the track record, and then they get high level. Yeah.
Okay, thank you.
Okay.
So, I'd like to welcome our second speaker, Anders Landsner, who's a computer science professor from KTH and Stockholm University. And somewhat on the same theme, of course, Anders will talk about how we can use simulations to understand how our own limited, as we now understand it, brains work. Welcome.
Okay. Thank you very much. It's a pleasure to be here and to listen to these fascinating perspectives. Yes, I will not speak exactly and directly about AI, but I will talk about the brain, which is, as you know, the only truly generally intelligent system or object so far that we know of. It may change. And I will talk about how we use and how people today use computer simulations to help us understand this very complex object, which it's obviously. So I want to give you some glimpse and some understanding of what is going on in that direction. So first, a few numbers updated recently, because these things change a bit. But anyway, the human brain has about 86 billion neurons, and the core. This is 10 to the... It's 1,000 millions. Yeah, 10 to 9.
Is it 10 over 9 or 10 over 12?
It's 10 over 9. Yeah, here. Okay, sorry. 10 over 9. So, okay. The cortex, which is what we think the highest functions reside, is the main mass of the brain, but has apparently bigger neurons, so fewer, bigger neurons, and therefore fewer for the mass. The number of synapses, this is the connections in our brains between neurons. They are very many in the cortex, 10 to 14, unknown what it is in the whole brain so far. They are very many. They are extremely important because there is, for instance, the site of our memories. So synapses is where the memories are stored, and without them we would be helpless, I think. It's an extreme... Oh, sorry. Now I skipped over things here. It's an extremely sparsely connected system. Like 10 to minus 4% of a connection matrix is filled. Anyway, the total length of fibers, axons, big fibers in the brain is about 180,000 kilometers in each of our brains. It's quite astonishing. I compare to the big supercomputers today have on the order of 1,000-kilometer cables, so that's a bit less. The power consumption of the brain is about 25 watt, and for large supercomputers it's order tens of watts actually. We have, as we heard, there are floods of data today, and the data about the brain is growing tremendously, and I can just show some small glimpse of what type of data we have. So here is an image of a nerve cell in the cortex. Its branching is shown. It's quite a complex shape in itself, though it's just one of these many cells. We have the synapse is extremely complex molecular machine, which takes care of signal transmission and learning, plasticity, as I said. It has 1,000 different proteins, so it's a machine with 1,000 different proteins, so it's really complex. And then we have new techniques to visualize parts of cortex. This is a small part of the hippocampus, and this optogenetic method called Brainbow can color the different cells differently. So we see the complexity in this very small part with the cell bodies and the processes, axons, etc., where the connections are. So it's extremely complex. So how can we think of this and hope to understand it? Well, I will give you a picture of sort of very abstract picture of brain computation or brain information processing that has emerged. Basically, this is a sensory, an input-output system. So we have senses, obviously, we have motor output, we do behavior, and in between something mysterious happens. The sense, I don't master this. The sensory parts of the brain are here in the back, vision, etc. The motor strip, which forms behavior, but there are many sort of unknown or territories which are called association areas where memories reside, etc. So what is a mental object in this kind of a structure? Well, the picture has emerged that something, a mental object, something we see or something we think about, is a sparse pattern of activity. This is a very small brain, obviously, but a certain mental object is characterized by a certain pattern of activity, and it can be distributed over larger parts of cortex. These cell assemblies are formed by learning, by this plasticity and formation of the synapses. So the network is rewiring all the time, actually. This network that emerges from our experience, it underlies, for instance, something called pattern completion, which is a Gestalt perception phenomenon. And we can see a 3D image, though we projected here is just a 2D image. There is another pattern completion, familiar, I think, to most people in Stockholm. So they have associations here because they've seen this. Others may think this is something strange. So this is Viking Line, the ship company's logo. There's also perceptual rivalry, which means that we can only sort of perceive either the vase or the two opposed faces. And that has to do with the dynamics in the networks in the brain. And these things underlie our ability to recognize objects in cluttered scenes. So these are in a way, fundamental sensory capabilities of the brain. In the auditory domain, you know this cocktail party effect, where you can distinguish, though it's very noisy, you can listen to one speaker. So this amounts to an associative memory kind of organization, and you can over time build sequences of these mental objects. So, and by that we can predict, build world models of what will happen next, etc. So the person, for me, who actually, and for many, who coined this and suggested this kind of views is Donald Hebb, who was Canadian neuropsychologist, and wrote a book called Organizational Behavior, for instance, where he described his theories. Eventually, this perceptual things end up in a decision-making and motor output, and these processes are also very intricate and complex. Right, so again, about mental representations, a few words. The brain, the cortex has an average spiking activity of only 0.1 hertz. So one spike in 10 seconds, if you see it over the whole brain. It is distributed, as I say, but these mental representations, when they are activated, they are much smaller than the cortex, obviously, but still have many neurons. And here, for an active cell assembly, some of the cells in that one are firing much more faster. So, and they suppress other activity. People have measured in the memory parts of the brain, the cortex, and seen things called Clinton neurons and Homer Simpson neurons and stuff. So you can find neurons that are specific to, for instance, a person. But they can be triggered by images of different sort and even when talking his name. So they are invariant in that sense. And there are no grandmother cells because there are still very many neurons representing such a concept in the brain. And if you think of this then over time, when we associate, this activity of distributed cell assembly is sort of morphing over time, and that is what I think we can call thinking in an abstract way. So this is a very complex system, and to understand it in any sense, I think, and many with me, that we have to use computer simulations, and that's what I will get to. So if we are going to simulate such a thing, what do we do with this tremendous amount of information we have? Yeah, the way, and here I think this creativity and the human ability to see relevance and ask the right questions is extremely important, because you will see that the models, the mathematical models of these objects are much simplified, and still the models replicate some fundamental activity in the system. So we have, and in the community, the focus is very much on finding out what of all this information is critical for understanding network operation and dynamics. Since we want to understand the signaling and information processing. So for spiking neuron models, a model of such a thing, well, it integrates its input from all these synapses coming in, thousands of connections, and it generates perhaps a spike, an output spike, which is transported to its target cells. And this signaling is via these synapses. So we have to model the signal transmission and the plasticity in the synapses. I mean, there are many other things going on in cells than these critical for. So we discard all of those for simplicity to be able to handle the model. People use different levels of complexity of models. I will get to that. But then we can ask what is the computational demands for simulating, for instance, a full-scale model of the cerebral cortex of the human. So I've calculated that a couple of times, and I show it here. So assume that we want to simulate this network, that size network, let's say not exactly the complex architecture, with a time step of 1 millisecond. Then we can calculate the memory required for each neuron, the amount of computation per second required to update the state of the neuron, and it amounts then to like 100 teraflop. If we have that, we could update the neurons. But the synapses are pretty much more. So, and they are actually in the models we have almost as demanding computationally as these. So the total, if we add up the memory, it gets 1 petabyte of memory we need to represent the state of the synapses in this network, and we need 60 petaflop to update it. And we even have to optimize computation. And what about computation, communication in this system? It is nerve impulses, spike events. That's the most important. And the average, as I said, 0.1 hertz per neuron gives 10 to 13 synaptic events per second. Okay, so the other side of the coin, the computers we use to simulate these things. So we can look at the top 500 list of fastest supercomputers today. So the latest one is from June. Then this Chinese computer was top of the list. It's from China National Supercomputing Center. It has almost 11 million cores. It has 125 petaflop of nominal compute speed. Its memory is 1 petabyte. Interconnect bandwidth, 70 terabyte. And terabyte now is 10 to 12 byte. And the power consumption is 15 megawatts. So that's quite impressive numbers. If you now put these next to each other, so the human brain model of the cortex size and this machine, you can see that memory-wise, it can fit computation-wise as well, actually. Interconnect-wise, you have even a margin, if depending on how big these events are, but they are small. Power-wise, if we compare that, we can see a very big difference. So we can conclude with this that it seems to be possible already today with this rather simplified network model, after all, to simulate a human cortex-sized network, I would say, in real time on this kind of machine. It hasn't been done, and typically in the community we do very much smaller pieces of brain simulations. We have included plasticity and learning here, and to note only that these two are the brain and this computer are very different in terms of, for instance, parallelism. So the brain, depending on how you see it, but if you see the synapses as the real processors, which I think is reasonable, then it is 10 to 7 times more parallel, and all computation is local. So memory and computation is always local. So this is an interesting feature. So I want to show you now a little bit about what these models that we use look like. Just quickly going through so you get a feel for the complexity. So this is a neuron, a real neuron. It can be modeled at different levels of complexity, from very simplistic neural units, which are not even spiking, to integrate and fire neurons, and to complex biologically based neurons. So it's just to choose. We often find ourselves here these days. But if you want to do the branching, you can build an equivalent electrical circuit of a branching neural structure with resistors and capacitors, basically. And you can do the same if you do the ion channels and have the equation, Hodgkin-Huxley equations. For that, it gets into an equivalent electrical circuit. So if you want to now simulate this, it's very much similar to simulating a chip on silicon, for instance, or some analog electricity. So it's well known. You use a lot of differential equations, and you can get a very good fit between the real neurons signal processing and the model. The synapses, you can actually do the same. I don't go into detail what these represent, but it's an equivalent electrical circuits which can be mathematically described very well. So the signal transmission in the synapse here, this is the cell, the synapse to the target cell, that is well described actually. But the plasticity and the learning capabilities is much harder to understand how that works quantitatively. We don't have very much information there. So in our system where we want to simulate this learning, we have used a spike-based learning rule, which changes the synapses between a sending source and a target cell, source and target cell. They are both spiking, and just to see, what you can just see is the number of differential equations, very simple ones, but still, in this case, 8 or something. That gives the final, given some activity, it gives the strength of this synapse, and according to these equations. So it's quite complex, and we need to simulate millions of those. Right, so now I will describe I'll come to a certain simulation and show some output of that. But first saying that typically we simulate a small patch only of some millimeter square or 2 millimeter square. We can, in our case, we have a modular network. This shows the cell types from the side. We have pyramidal cells, some inhibitory interneurons that are important in the brain. And we put them in small modules called mini columns with 100 neurons, and in bigger modules, not so critical. Then we impose a memory on this, or we activate the cells so that a memory is formed by this plasticity we simulate. To note here is the connectivity here is very highly recurrent. This is a very loopy graph, if you like, which is what you have in the brain. We have excitation and inhibition, so it's exciting and inhibiting activations, and this gives a certain kind of attractor dynamics called attractor dynamics. We have an attractor network which underlies these perceptual operations, completion, rivalry I was talking about earlier. This now shows some output, what kind of output you get when you simulate and solve these differential equations. So you now have, this is a small network, but you have time here. You have the cells here, and for each line there is a specific cell, and when it gives a spike, there is a dot. We have implanted a number of memory patterns in this network, and the network dynamics jumps from one pattern to another over a couple of seconds. So this is 3-4 seconds. So that's simulation output from such a network. We can now synthesize something which is similar to EEG. You can measure EEG experimentally. So from the model, we can synthesize EEG. We can, on the other hand, look at single neurons and how they spike and what membrane potential they have. So from macroscopic to microscopic, and we can process this information in any way we like, actually. So this is example output, and this is what we do. So our memory systems are quite complex, much more complex than the deep learning networks. I can assure you that there is short-term memories, there are long-term memories, there are hippocampus and memory consolidation and stuff. So in the brain, many processes are involved in forming these memories. One very important key component in cognition, in our thinking, is the short-term working memory. That's where we put things. If we have a problem and we look up data to background data, we put it in our working memory, and then we elaborate and reason about it. If the working memory doesn't work well, you cannot be very effective in this kind of operations, and it is in fact a key component in cognition which is disturbed in many neuropsychiatric and neurological conditions. Yeah, prefrontal cortex is mentioned as a main site here. So what's interesting is that the theory about how working memory works is now changing right now, basically. So it has for 20 years been thought that long-term memory is not at all like working memory is not at all like long-term memory, because working memory is ongoing activity that is triggered by some inputs. But that has been more and more problematic view. So now there is a new theory coming up which says that long-term working memory is like long-term memory. It's actually based on very fast synaptic plasticity processes. And in fact, that idea has been around, but in the past few years, it has been found experimentally that you actually synapses in the brain could change on seconds. I mean, it's much faster than was thought before in some areas, especially this prefrontal cortex. So we wanted to simulate this, and that's what I want to show you. So this was a paper published this year. So it's a simple word list learning. So you just have a number of words, in this case 12. They are read aloud by some speaker in a rate of 2 seconds per word. So it's 12 words, takes 24 seconds. And then the test is that you have to freely recall in any order as many of those things that you could remember. And we simulated this in a network with 6,000 neurons, 13 million plastic synapses, time step 100 microseconds, and each word of these 12 was then coded by activity in 480 pyramidal neurons. So it's really a small model, as you can imagine, but it has some interesting dynamics. So this is again a raster plot here. So here we see these 2 seconds. Well, it's actually just 1 second when the word is presented to this simulated network. The word, I mean, it's just a pattern of activity. Then what happens is that this network spontaneously recalls this word. So it's thinking silently about this word, basically. And we can see that activity, and we can see some fine structure of that activity. So that's with one single word. If we now do the test of training the network with 12 different words, then each word here is time still, each word is represented by a pattern of activity which actually extends up here, but we see a small part of it. So every word comes every second, every 2 seconds. And that's for this phase, and then there is a free recall phase of the network model, where we can see what items are remembered. And there is some interesting dynamics here, because actually if you do this yourself, you will see that you actually try to repeat the first words in the list while the next are coming in order. And that's exactly what this simulation shows, this repetition. And you can also see that words that are repeated many times by chance, more or less, they are also remembered. Okay. Then you can do lots of measurements of this. I skip that. But now we compare how does human do. It's well known how humans do in this case. So if you take the 12 words in order and measure how well a human can recall them, you get this U-shaped curve with something called primacy, because you remember the first words, and recency, the last words, and those in the middle are not so good. This is exactly how the simulation behaves as well. You can also test conditioned recall, meaning to nearby words, how they are recalled, and that's also copied, reproduced by the model. You can cue, if we look at this one, the words that were not recalled here, they can, if you give half of the word, you give a cue, a little hint, then the system can recall all the 12 items, which also humans do. Same here. You can look at microscopic level. Now I am short of time. I will speed up. So the important thing is you don't just have this function which corresponds to human behavior. You also can look at every little detail. So this is at the synaptic level. We can make sure that the potentials from a single synapse incoming pulse is actually of the same size as in real brain, because this can be measured. So we are confident that this can actually happen. We also see in this kind of simulations, we see oscillatory activity, oscillations over time, which can be measured by local field potentials. So we do connect to lots of different data at different levels, and that's sort of the idea with these things. So I will soon finish, but first one slide on comments of this. So that is exactly what I said. These simulations have the ability to bring together many different kinds of data into a working model, and I think that you cannot certainly do it experimentally, and it's very useful to have a working model of a system. So with that, you can define maximally informative experiments, and that's of course can speed up progress in understanding when you enter into a modeling experimentation cycle. Also, I said, yeah, since working memory is important, obviously we need to understand it, and it seems that this new theory is really doing quite a good job, actually, compared to simulations of the older one as well. And what we also can now do easily is to let working memory and long-term memory interact, and this is our ongoing work. It's quite very exciting, actually. So talking about, well, more connecting to today's theme, maybe future AI systems need working memory of some sort like this when they get complex enough. All right, so some conclusions. Computers, supercomputers, especially for large-scale simulation, they are excellent tools. They can build, they can simulate almost full-size network models today. They will be more capable tomorrow. Simulation will speed up understanding, and which will have a major, this understanding itself is of course very important for curing diseases and brain disease and what have you. And this kind of specific model that I was describing, it did quite a good job to replicate this memory phenomena. Okay, so impact on AI, I'm not sure. It's not at all certain that the brain, what it looks like, should really be the way that future AI is designed, or AI systems, but you can get information about how to build a efficient associative memory with temporal association, integration of different memory, different time spans, and brain chips actually are already there today. They don't have learning typically, but the extreme parallelism of brain systems make it favorable for this kind of thing. I thought I had something else, but all right. Acknowledgement. I want to mention that my colleague Pavel Herman at KGH is doing a lot of this work. Former PhD student Mikael Lundqvist Filtali. Florian Fibisch is now working on this long-term memory, working memory model. And the funding from Science Council Swedish and EU has been most important. So, thank you very much. And over time.
Fascinating. Let's open up for questions to both speakers. They're a very shy audience. Yes?
Yes, you were comparing the human memory with...
Microphone, yeah.
I'm sorry.
We're streaming this.
Okay. Yes, you were comparing your memory with the computer memory.
Yes.
You even used the measurement byte. But byte in the traditional computer means binary units.
Yeah.
You know, it's but I don't think that we can say that the human mind, the human brain, has a binary architecture. You understand what I mean?
Yes.
That
okay.
all information element is just built up by binary.
No, of course not. No.
No.
Right. I agree. But actually, it's quite well known. If you have an associative memory, there is theoretical work of how much information you can store in an associative memory like this, and that is measured in bits. So you can actually, even if the system is analog, you can measure its ability to store many patterns in terms of bits, actually, and that people have done, and that's what I refer to.
Are we quite certain that the human mind is working analog, in an analog fashion? Or is that just a microscopic view of it? If you go into the small details,
yes.
It might be binary elements. Wouldn't that be possible?
Ion
maybe.
channel movement is pre-binary, right?
What?
Ion channel movement is pre-binary.
Yes,
yeah,
yes, but they are stochastic and they are integrated over time because the cell membranes
analog,
are very slow. So I think there is a lot of analog things. What is interesting is that on the cognitive level, we either recall something or not almost. I mean, it's very all or nothing in the real macroscopic behavior, and that's because these attractor dynamics according to theorem.
Question to Hirokai-san. You talked about this Go program that was learning very fast to play the game in a few days or so. And the speed one could consider being the computational power that is available, CPU power, memory power. What about the software here? And if you were to go backwards to a simpler computer, could you still run the same software on it? And what is your prediction about the future? How fast the development will be of the computer power to match this development?
Well, I think it's interesting in a way that the AlphaGo Zero, which actually just published, actually use a much smaller number of hardware. Actually, that's only for TPU, so that technically you can just put in a desktop actually. And then the major part of this progress is actually software improvements, and the network actually dramatically simplified. And that actually is the key that you actually, for the AlphaGo previous version, which actually beat Risedo, was that requires like 150 TPU or something, like a relatively large number of processors. Actually, now go down to the 4 TPUs. So I think the hardware progress is really key factor because it's moved from the conventional CPU or GPU to the TPU. That's like dramatically reduce the resource requirement for the hardware because of the new architecture. But at the same time, like it's much more than that. Actually, the improvement in software architecture actually impacting dramatically to the actually computing requirement and resource requirements and the things we can do actually. So that part actually, they have to go hand in hand, but actually has very interesting progress because like a hardware progress actually fostered the new kind of software architecture, and then the software actually improvement actually dramatically increase the utility of the hardware as well. So that's, and then we haven't yet to see what will be the next generation hardware. We are in a very exciting period because the things we do in the past have dramatically changing now, and everyone really going to neuromorphic computing, and then some other kind of computing. We're yet to see which one is actually right. And then one other thing is actually people trying to actually create a human brain-like computer, and part of that actually we can probably get inspiration, but I don't think that is the right way to go unless you want to actually do scientific research to actually understand the human brain. That's fine, but like if you have to create like a superhuman intelligence, and we probably have to go with something else. Actually, we probably inspire the human, but probably redefine the process and completely augmenting it. So that's something to be very interesting, and also like interesting because like when I asked Andre's talk, one of the utility of the model that he's building is probably understanding of the human behavior and working memory is one thing, but like I'm very curious to understand if you give a stress to the model, what is actually the limitation of the human cognitions that can predictably come from the model that you created, because we haven't evolved to most of the evolutional actually optimization is we evolved to actually survive and reproduce, and the science is relatively recent. I would say it's like remarkable we can do the global science because maybe because we invented language, we evolutionarily acquired the language and the writing, so we can actually externalize the memory, so that we are not really constrained by the working memory. We externalize the memory, and at the same time that gives some constraints, which I mentioned, and because of the language, and then so like what is actual limitations of our native cognitive capability, and then what is the limitation even if we externalize the memory, and then what is the solution for that? That would be the interesting, and that could be back to your questions. And what would be the software and architecture, because like that's a big architectural change is happening of the cultural and evolutional sense.
No, yeah. Okay. Yeah, I wanted to comment that, of course, but superhuman intelligence, yeah, we don't know what will be the route or if there are different solutions to that. But one, it can still be superhuman if you are able to build hardware that is much bigger and faster than the human brain. I'm not particularly fond of this perspective, but you could. I mean, there seems to be no limitation of that sort.
Yes, thank you very much for your presentations. I just have a quick question. Like right now, one of you is trying to create the best brains, the digital brains. One of you is trying to understand the brains that we have right now. And as was just talked about, we are talking how can we actually create the best human brain possible from the different machine learning things that you have talked about, not just trying to model the brain and then create a better one from that, but to actually create something much better. Have you talked about how this could sort of be implemented on the human species or so forth with like new CRISPR technologies and so forth? If you create a perfect superhuman brain and we have a perfect understanding of the brain, could you then start to change our own protein structures to implement those kind of brain structures on humanity?
I think that's a very interesting question, because like if we understand like how you augment capabilities, and which is not really in our genetic codes, the brain formations, and they got the CRISPR-Cas to actually modify the brain structure so we can augment. Of course, there are all the ethical issues, and they put just aside for now. But I think like we're going to do that in the future. If we understand this, like okay, if we actually increase the number of neurons and working memory, and they get some kind of new kind of wiring system, and if we can actually understand how we can developmentally achieve that, I think we're going to do that actually. Then the question is like, if we're going to get brain, if we're not going to get the brain, that of course, like I'm not. It's not the technology we have immediately, but of course, like we have CRISPR-Cas, and then probably it's possible that in the future we'll be able to do that. And now also, like we start having a technology that we can actually create a sperm and an egg from the iPS. And then there's in a mouse in a very early study, very successful in Kyoto and Kyushu University. It's published in Nature last year. And the success rate is very low at this moment, but that can be a matter of technology. And they put the CRISPR-Cas, and they get this change. And that's, but if I apply to like, not just human, but like other species, they might be able to talk, and then it could be super intelligence, and then you know, there's a movie like you know, the Planet of Apes. You know, so we gotta be a little bit careful which one to apply. But
thank you. Given the discussion here, if the human brain was digital or analog, I would like to know from a technical point of view, how would you represent knowledge in an AI system using the latest or a more modern system you have today?
How would I represent knowledge in a system, a brain-like network, you mean? No, but yeah, it is the key to that are these cell assemblies. I mean, that is the representation of knowledge. What I didn't say is, of course, the brain. You can find these hierarchies that you have in deep learning networks. You can see signs of that. So this is a relevant way of doing it. But I'm missing a lot in deep neural networks. For instance, all the cross connections, which are more than 95% in the brain, in the cortex, and so I would represent it partly as in a deep neural network, but with more cross connections, more different areas for auditory, visual, motor, etc. So it's network activities, yeah.
How would you represent it?
No, I mean, I think like in a way, like a current deep learning network is more the task specific. You know, so where our brain is more general capabilities, and that's a cross connection that probably have a quite substantial function in the cross modality, the cross functional thing, rather than task specific thing.
But cortex is actually very similar in even motor and sensory, but especially sensory areas and memory. So it is a generic computation, generic statistical machine, I would say, that you can represent all different modalities and motor things, etc.
Yeah, I wouldn't surprise like someone come up with like a engineering version of their cortical cross connections in a you know, computational trainable way, and they got a much more you know, general performance neural network. That could be another breakthrough which might happen in the future.
Yes, a question to you, Hiroaki. If we consider a future scenario in which we have AI to generate a vast amounts of hypotheses and we can test them all, would you imagine that we would converge on a truth in science, or that it would diverge in an explosion of complexity and so on?
But with like a diverse, you know?
Yeah. For example, like different fields of science would arrive at different paths and stuff like that.
I'm not sure if I understand your question right, but I think if we start having like a lot of you know, AI system discovery, I mean, you know, it's just like a, you know, probably like a, you know, AI, you know, the scientific process is not gonna change that much actually.
Okay.
At this moment, probably we're gonna have a tool that actually speed up the discovery. Rather than actually, we just like, you know, put this machine, okay, this is the data, and then now this area, just to give a hypothesis, and then now all the verification and support evidence. That's probably the initial step. And that steps, we're going to have a tools, not just to do computing, just to do all the, you know, hypothesis generation, and then the support logic presentations, and then run the experiments, right? So that I think would be a very useful tool, you know, and then each area that would be used. And sometimes like you use a system in biology, the same system run a chemistry lab, and then if they start talking to each other, that would be very interesting, because that knowledge, which is very difficult in cross-disciplinary today, I mean, you know, a lot of government agencies try to do that. It's not very difficult actually, because in depths of knowledge we require and experience we need. But if, like, you know, machine can talk to each other, and they present in a way that's, these two areas that can fuse and they get the new hypothesis, which never able to do it in each field alone. And that would be probably initial value. Of course, like, whether this is a personal, agency, whether we can fool the Karolinska professor, it doesn't really matter. I mean, that's kind of like the final part. But like, I think the real value is to create a system that accelerates the science. And I think that would be very interesting to see the new opportunity, because there are limitations on the human lifespan, the experience, and the resources we can get, and then attention we can get.
Yes, this is a kind of open question to both, but also kind of specified to Dr. Kitano. The question regards the relationship between art and science, and you use an explanation of Beatles, and you're saying that they'd never explored the full potential of how Beatles can sound like, and I'm wondering, isn't it about the core, not the whole context?
I mean, for the core?
So isn't it rather to find the actual core of Beatles, what they would try to communicate, not the full extent of how they can sound like?
Yes. So that actually have to go into the more the contextual understanding of the Beatles. And that example we showed is, we are not talking about that core. We're just like more on the stylistics, actually. So we understand about the style of the Beatles and then how we can actually apply that. Of course, there are the lyrics, which I haven't talked about. And then what's the cultural context why Beatles composed the music at the time? I mean, and that actually we haven't talked at. I mean, I would rather save that for the human civilization rather than AI to do it.
I'll give myself the privilege to ask the last question, I think. So, there are many Nobel Prizes. There are the different natural sciences prizes. There's the literature prize, peace prize, sort of half fake economics prize, and so on. You talked mostly about the sort of natural sciences here, but which of all the Nobel Prizes do you think the machine would have the largest chance of getting?
Well, it's interesting because but I'm kind of interested in physiology and medicine because I'm spending time on this. But like chemistry and physics, actually, because it's much more solid, theoretical basis than the biology. Biology is way more complicated. In one aspect, I think I have a much better chance in the chemistry and the physics, I would say. But at the same time, it's very interesting. The same discussions on the Nobel Dialogue in Tokyo about the future of intelligence. And the last panel with the 5 laureates, the CEO of the Nobel Media, he asked questions that, did you think, if the laureate think like someday like AI will be on the podium, just like those laureates, and then one laureate says yes, the other laureate says yes, but not next to 50 years, and the third laureate is interesting, yes, but literature prize first. And he was not the literature winner, obviously. But so that's, I don't know, I wouldn't comment that on whether we're going to do that in the literature, but it's, if, with a fake authorship and in the literature, that's maybe possible. But I think like a science prize, I would say like a chemistry probably, but I think but I'm not really knowledgeable in the chemistry much. I mean, I'm spent more time in the biology last 20 years. So like, we see a lot of issues in the biology that even a part of them solved by the AI, but accelerated, will save a lot of people's life and solve a lot of high impact in society. That's why I'm really targeting for this life science.
Do you want to place a bet, Anders, as well?
No, thank you. I don't do that.
Okay, I'll put my money on economics, actually. With that, I would like to thank both speakers and the audience and everyone who's been watching us online. Thank you very much.
Thank you.